Today we'll be talking about um, AI training and also sort of inference of large language models on Aurora, how to scale that up, what tools to use, and best practices to use our systems. We're also going to start with the Intel Python packages to sort of lead into the AI frameworks, and this talk will be given by different members of the data science team at ALCF. Myself, I'm Ricardo Balin, but we'll also have Filippo Simini, Khalid Hossein, Sam Foreman, and Sid Raskar. And then the other thing we wanted to mention before we get started is just because we'll be switching through a number of topics, if you could please put questions in the chat and we'll do our best to address the questions in the chat as they come up, and then we'll leave time at the end to make sure that anything that was not answered will be answered. Um, okay, so then with that, then perhaps we can get started. So the first thing we wanted to cover is what I mentioned, this data parallel extension for Python, also called the DPEP. This is really Intel's Python stack for programming on heterogeneous devices, which it does include Aurora CPUs and GPUs. And it's composed of really three packages, DPNP, their data parallel extension for NumPy, DP control, data parallel control, and then Numba DPEX, which is their data parallel extension for Numba. For all of these three packages, the programming model that Intel decided to implement is what they call compute follows data. What this means is that the user or the programmer really just has to offload the input arguments to the library call or a particular kernel, and then the target that the execution is following then the data. So what this means is that when you call a kernel or a function, there's really no need to specify where that function runs. It infers that directly from the input data. And then the output data is then returned and allocated on that same device. So really, the user, the programmer, just has to worry about allocating the data on the proper devices, and then the rest of the execution will follow those input arguments. Also, with these three packages, there is interoperability with the AI frameworks through DLPack. What this means is that you can do zero copy data access both from CPU and GPU of any allocated array. So for example, if you're trying to go from NumPy to DPNP, this of course would be through the CPU, you could do a zero copy data access. Or if you're trying to integrate DPNP or DP control with PyTorch, again, this would allow you to allocate arrays with DPNP and then provide a zero copy view of that to PyTorch. Unfortunately, this is not yet available in TensorFlow, but it'll be upcoming. The other thing I wanted to mention as we keep going through this talk is to please refer to our documentation as always, and we do have a getting started repository where we put the material for this talk. And the getting started repo is also linked in the Zoom chat. But we're trying to give an overview and best practices and sort of highlight the key items. But if there are more details in both the documentation and the getting started. So first, how do you access these Intel packages for Python on Aurora? Well, for DPNP and DP control, it's very easy. They are included in the base frameworks module, the conda environment that is provided with that. So all that needs to be done is module load frameworks. And then, for example, you could run a simple conda list and then grep command to see what versions are available with that particular conda environment. To access Numba DPEX, that currently requires some additional install steps. These are all outlined in our documentation, so we would refer you to that. And then also the Getting Started repo has actual scripts that you can run to install these, basically following the documentation, but it actually provides script that you could run. So let's start going into some of the details of these packages. So first, DPNP. The goal here is to implement a subset of NumPy in DPC++ or SYCL. So this is intended really as a drop-in replacement for NumPy. So this is very similar to what CuPy would be for CUDA devices. And so this we would suggest as sort of the first layer to port NumPy and CuPy code to the Aurora GPUs. So you can see sort of this is the type of replacement that you would do in your code to replace NumPy with DPNP. But we do sort of recommend that users follow this. There's a link here in the slides that will be provided to a comparison table that is in the documentation for DPNP. And this covers the current API coverage of DPNP relative to NumPy and CuPy. So we will say that they have a lot of coverage. Intel has provided a lot of coverage, but some perhaps niche functions may be missing. And so, this is meant to be a drop-in replacement, but there isn't 100% coverage yet. Um, DPNP does support reduced precision for floating and complex and integer numbers. For example, you can do FP16 math, and so that gives good integration also with maybe things like PyTorch. And the other thing to mention is that DPNP does leverage oneMCL in the background to do performant linear algebra on the PVC. So you can actually get quite good performance using DPNP on GPUs. The other thing, maybe here we can cover a very quick example, just to point out a couple things. So this is just doing a sum with DP&P, but as we call this NP as array, just to allocate an array, there's a couple things that we wanted to point out. The first is that actually the array is created on the default SQL device, which this is the PVC on Aurora. So you can actually, by default, you don't have to specify to allocate on the GPU. That is actually the default behavior. And then the other thing is that when you allocate an array, a SQL queue and a device object are created and then are carried around with the array. So for example, after allocating X, you can then query the SQL queue associated with X as well as the device associated with X. And then if you're trying to just sum the elements of X, you can call np.sumX and that returns Y. So here, again, following this compute follows data programming model, you don't actually have to specify where np.sum runs. It'll run based on the device of X. So in this case, it'll be the GPUs. And then the other thing is also the output array is allocated on that same SQL device and then is associated with the same queue as X, the input. Now, DP control, this is really the library that we use to access devices supported by the DPC control, DPC++ runtime. And so what this means is that we effectively in Python now are exposed to features such as device introspection. We can create specific SQL execution queues. We have more control over memory allocation, and also we have some control over kernel creation and submission from oneCCL code. And so this is sort of a way to effectively explore the devices available and integrates well with DPNP, but it gives finer grained control on some of the things we saw in the previous slide. The other thing that DP control provides is a tensor library that is also implemented in C++ and SQL. So this is very similar to DPNP. This is though what actually follows the Python API standard, which gives interoperability through DLPack. But other than that, it's really similar to DPNP. And in fact, DP control is a dependency of DPNP. So these two packages are very connected with each other. Again, there's more examples in the getting started and documentation, but we wanted to highlight maybe some key usage of DP control. So for example, here, this code is doing very simple sort of device selection and then creating a queue for each device and then allocating an array on each device based on that queue. But here we highlight sort of the key commands. And so, for example, you see at the top, we are using DP control to get the available devices. And here we can filter by device type. In this case, it's the GPU. And then we can loop over that list of devices. And then for each device, we create a queue with, again, DP control. So here we call DP control.SQL queue, specifically passing that device ID. We can store all those queues in the list. And then for each queue, what we can do is then just have a simple function that allocates an array. In this case, we're using DPNP. You can see that we're passing that queue as an argument to the dpnd array function. And so this means that we are allocating an array specifically associated with the queue that we've previously created. And so again, this is pretty simple, just in the interest of time. But this shows how DPNP and DP control integrate together to give you sort of fine-grained control over where the arrays are allocated, what device, and what queues are these arrays associated with. A couple other details about DPNP and DP control. So as we saw from the previous slide, the array creation APIs take other arguments. And so one was the SQL queue. They also take directly a device ID, but also you can specify the memory type that you want for that allocation. And so, for example, if you wanted to allocate an array specifically on GPU 1, you would be able to pass that string GPU:1 to the DPNP as array function. Or if you wanted to put it on the shared memory, you could specify that again through the array creation function. The other thing to point out is that by default, only the GPUs are available as SQL devices. Those are the default SQL devices. And so that's because the default environment sets oneAPI device selector to only see the GPU. However, you can still access the CPU. All that you would need to do is change this environment variable oneAPI selector to include both the GPU as well as the CPU. So then you would have control over both the CPU and GPU and be able to allocate arrays specifically on both devices. Also, another thing to point out is that the machine learning frameworks module, so that's what happens when you do module load frameworks, sets this other environment variable, ZE flat device hierarchy to flat. What this means is that each tile on the 6 PVCs are visible as distinct devices. And so DP control sees 12 devices. And so that's something I wanted to point out in case you, if we go back to the previous example, this sort of first highlighted line returns 12 devices, not 6. And then the other thing is that since DPNP version 0.15 and DP control version 0.17, all the kernels run asynchronously with linear ordering. So this is very similar to CuPy. What this means is that just be careful when you try to time kernels that you need to actually put a wait on the SQL queue of the output array or the function call. Otherwise, what you're really timing is just the kernel call, not the actual execution of the kernel on the device. Now moving on to NumPy-DPEX. This is really just an extension for Numba. So if you're familiar with Numba, it should be fairly similar. And the idea is to generate performant parallel code on Aurora's CPUs and GPUs with NumPy-JIT compilation. So they provide a Python kernel programming API called KAPI, and this is using an LLVM-based code generator. And it does integrate with NumPy, DPNP, and DP control. So what this means is that the kernels can take in arrays defined in either of these 3 packages. And again, it follows the compute follows data programming model. It also offers a series of different types of kernels for increased complexity, range, and ND range. And there's links here to the specific documentation for these 2 with examples. You can also create device callable functions that you can invoke from these range and ND range functions. And then finally, to see exactly what packages, DPNP and math, and also what precision are supported, we do refer our users to the documentation for NumPy-DPEX, where there's a full list of all that information. But again, sort of we, just in the interest of time, just go through a pretty quick example. In this case, we're just doing a sum with NumPy-DPEX. And so you can see the first thing we do is we decorate a particular function with dpex.kernel. This will tell the compiler that this is the function to optimize with NumPy-DPEX and parallelize. The other thing that's important is that we need to get the work item for within that function. And NumPy-DPEX follows the single program multiple data programming model. So this means that each work item then runs this particular function for a subset of the input and output arrays. So you can see in this case, we're getting work item I, and then we're really just doing the sum over element I of the arrays A, B, and C. So at the bottom, you can see how you would then allocate those arrays with DPNP. Again, the default SQL device is the GPU, so this is running on the GPUs. And then you call the function vecadd with dpex call kernel. And the other thing that's important is you want to define the amount of work items available. And so you do that by specifying a range, in this case of n items, which means that the work item is basically one element of these arrays. Okay, so this is the quick introduction on the Intel Python packages and how to program the GPUs with Python, and we'll now move it on to the AI frameworks.
Thank you, Ricardo. So take over. Do you see my browser window?
Yes.
Okay, so next we talk about PyTorch on Aurora. and AI frameworks. And I'd like to present two main things. The first is how you can access Python and several of Python AI libraries like PyTorch and TensorFlow on Aurora. And the second is more specific. Once you suppose you have a PyTorch model that you trained on your laptop, how you can run that on one or more Aurora GPUs. So let's start with how you can access Python and several libraries of interest on Aurora. So we provide a pre-built Anaconda environment that includes libraries such as PyTorch, TensorFlow, Horovod, MPI4Py, and others. These libraries are all optimized for running on Intel hardware. The way you activate this Conda environment and can access these libraries is through this command module load frameworks. Once you do this command, you should have Python available in your path, and you can then import Torch and other AI libraries that are already pre-installed. Something to notice is that these frameworks module is periodically updated about every quarter. So every few months, this will change. We will have updated versions of the libraries. And the other thing to notice is that this environment cannot be modified. It's read-only. So if you need to use additional packages that are not present in the frameworks module, what you can do is the recommended solutions is to create a virtual environment, which is always a best practice with Python and when developing your Python projects. The other solution could be to clone the framework Anaconda environment. This will create a mutable copy of it on anywhere that you have write access to. However, we do not recommend this approach because it's time consuming and also takes up several gigabytes of disk space. So let's see how to create this virtual environment via Venv. So after you load the frameworks module, you can issue this command, python-m-vnv. Then you specify the path where you want to install your virtual environment. And most importantly, you should add this flag, -- system side packages. This enable the newly created virtual environment to inherit all of the packages present in the base frameworks environment. So they will be available in your virtual environment. Then you should activate your environment with sourcing this command. And after that, you can use pip to install any packages that you need. And there are also flags if you want to like install newer versions of some packages that's already installed in the frameworks. And you can refer to the Aurora documentation for more details. Okay, this is how you can have Python and many deep learning libraries available on Aurora without having to install them if you just need to use the basic ones. So now let's switch to focusing on how you can run and train deep neural networks on Aurora. We will focus on PyTorch, which is one of the most popular AI frameworks nowadays. Although we also have available other frameworks like TensorFlow and JAX present in the frameworks module. So focusing on PyTorch, we'll see how you can port the code that can run on a CPU onto running on Intel GPUs. And then later on, how you can use distributed data parallel within PyTorch to do data parallel training on multiple GPUs. First thing to highlight is that for the current version of the PyTorch that we provide, you have to also import this other library, which is Intel extension for PyTorch. This library provides optimization to the base Torch library, and allow you to run effectively on Intel GPUs. And it's highly recommended that you import this library right after importing Torch and prior to importing other packages. So let's see a simple example first. So here is you SSH into Aurora and you request an interactive session of 30 minutes on one node, and then you are on a compute node. So you can try out this example in the example folder in this repository. So the first thing we do is we load the frameworks module as we saw before. Then we type Python and we enter the Python interactive prompt. If you import the Torch library and you ask for the version, you can see that we currently have PyTorch 2.5.1 available. A few things that you can check to have an overview of the Torch packages and the devices available is to issue torch.xview is available. It will say true if PyTorch is able to see the GPUs. The device count will tell you how many PyTorch devices you have available, and in this case it's 12 because by default, so Aurora has 6 GPUs and each GPU has 2 tiles, and by default a Torch device is mapped to 1 tile. So in total, on one node, you have 12 devices. The current device, it will say that you are on device 0, so the first tile. And if you ask to print some of the device properties, you get the name, and it will tell you that each tile has about 65 gigabyte of memory and so on. So let's see now briefly, once we verified that we have PyTorch that works and it can seize the GPUs, how you can, what code changes you have to do to your CPU code to be able to run it on the GPUs. As we saw, the first one of the first things is to import Intel extension for PyTorch as IPEX. Then other things to change, if you have any CUDA call in your code, you should replace that to xview, which is the name, the Torch name of the Intel GPUs. So for example, any torch.cuda should become torch.xview. And then same for when you want to move models or data to a device, you should replace CUDA with xview in string. And then you can take advantage of the IPEX optimizations using IPEX.optimize, wrapping both your model and optimizer on this function, and this will give you optimizations and speedups. So here you can see an example code that you find in the example folder of this repository, where the green lines here are the things that I just mentioned that you should add to your CPU code to train. And as you can see, it's very minimal. Yes, as I was saying, .example, PyTorch DDP, you can find this example named PyTorch xview. You can see here a quick, an easy command that you can issue to check the usage of a specific GPU tile. In this case, you can see that tile 0 is utilized at 99%, while tile 1 is idle at this time, because we're just using, if we run Python and then the executable name, we just utilizing one GPU. What should you do if you want to utilize all 12 or even more tiles at the same time? You can use the distributed data parallel module. We also have Horovod available if you use that. But here we go with the distributed data parallel to do to distribute the data set across all of the devices you have available and perform the gradient computation simultaneously, and then synchronize the model updates across the ranks. So the first thing you have, additional code changes you need to do is to import the oneCCL binding for PyTorch. which enables the communication between the ranks via Intel's oneCCL library that provides efficient collectives such as all reduce to compute the average of the gradients altogether and all to all and others. Then we should initialize distributed data parallel along with the distributed sample to partition the data among the ranks, pin each MPI rank to a specific GPU tile, then wrap the model in DDP to keep it in sync across all ranks. If you want, you can rescale the learning rate and then remember to set epoch at each new epoch in order to shuffle correctly the data across epochs. So going back to our example, these are the additions. So again, some importing MPI for Pi and sockets just to be able, and all this part here is to initialize the communication between the ranks. And you have to as well import the DDP here. And as I was saying, the oneCCL bindings for PyTorch. After that, you can initialize DDP with the information you collected previously about the rank, the size of your, the total number of ranks. Then you pin each rank to a GPU. And then again, you use the distributed sample and the data loader with that sampler in order to distribute data across all of the ranks. Wrap the model in DDP. Here optional if you want to rescale the learning rate, and then the set epoch command. After you finish training, you can destroy close the communication that you opened. And so you can, an important caveat is for the current version of the frameworks, if you want to run on more than one node, you should export these three environment variables in order for it to work. Otherwise, you will see a hang. So this especially is particularly important. Again, you can run on, this time on 2 nodes, and you can see quite a speed up. It's, I think it's maybe several seconds faster. Now I hand over to Khalid, who is going to tell you some tricks and useful things to know when you want to run on more than 1 or 2 nodes, maybe 100 or 1,000. There are a few things you should be paying attention to, and I'll hand it over to him.
Thank you, Filippo. Now I will share my screen. So can people see my screen? It's a GitHub README. Can you see it okay? Anyone?
Yes.
Okay, thank you, Filippo. So I'll talk a little bit about the using AI frameworks at scale. By scale, we mean at large number of nodes involving a large number of GPUs on each node. So the major challenge of using the AI frameworks at scale, in a sense, using any Python Conda environment or a PIP virtual environment at scale is this dynamic library loading. So when we have a Conda or a PIP environment, it is located in some directory. It could be our home directory, or it could be our shared file system. So now when we try to do something simple like import torch at a really large scales, for example, 1,000 nodes, 12 GPUs per node, at that scale, when our Python runtime tries to read this library from a specific location, it creates a serious stress on the file system, and that can lead to hangs at large scales. And also, in severe cases, the file system may crash. So to circumvent such an issue, we have a solution called Copper. So Copper is a cooperative caching based application. So what Copper would do Copper would set a leader node for your large job, bring in all the necessary files to the RAM disk of the leader node, and then using a hierarchical algorithm, it will distribute it across all the processes that needs torch, for example, or numping. And we have done some scaling tests with copper, and we have tried to do it up to 8,000 nodes and 12 ranks per node without using copper. Just loading PyTorch from Lustre-based shared file system takes about 17 minutes. And with copper, it can be done in 60 seconds. And using copper is as simple as putting module load copper and launch copper.sh in your job script. So this launch copper.sh file is in your path by default, set by our admins. And then the second thing is to do is doing this line to your MPI exec, where you give the Python path of your Conda environment or pip environment by adding this little prefix to the path /tmp pointing to the RAM disk of your leader node, your username, which should be automatically picked by the $user, and /copper. After that, you put the name of the path of your Conda or pip environment that you would like to be distributed across. This should give you the ability to scale out to many hundreds and thousands of nodes. So we would recommend, if you are trying to go beyond 128 nodes, we would strongly recommend using this method to ship out your own Conda environment. If you are using just the frameworks module, which has a pre-built Conda environment, and we have tried to give a reasonable coverage of AI ML libraries. If you are using, and if your application runs with just that, then you do not have to use copper, at least up to 4,000 nodes. Any questions? Okay. So next thing is, so far based on our discussion, we have a PyTorch model. We have shipped it out to many nodes, and we can start our training. Now a little bit attention to the performance that we would be getting. To get a reasonable performance out of an Aurora node, we have to be mindful about the architecture. And this our Aurora architecture is such that we have two sockets, and each socket has a CPU and 3 GPUs, and each GPU has 2 tiles. So we can say we have 2 CPUs and 12 GPUs from the perspective of AI frameworks, because the frameworks module will display all the tiles as individual devices. So when we execute a Python script, or when we submit any job, we should make sure that GPUs 0, 1, and 2 are managed by cores from CPU 0, because they are in the same socket, and the GPUs 3, 4, and 5 should be managed by cores from CPU 1. And how the CPU cores and GPU cores are talking to each other could be seen by using module load XPU SMI from inside of a compute node, because our login nodes does not have GPUs. And then if we execute XPU SMI topology -m, we get the output where we see the CPU affinity. I'll zoom in a little bit more so we can see better. The CPU affinity of the GPUs. You can see GPUs 0, 1, and 2 has natural affinity with cores 0 through 51, which belong to socket 0. A point to note, we do not recommend users using cores 0 and 52. They are reserved for special tasks at the system level. And now, what if we do not do any CPU binding? So if we do not do any mindful CPU binding, the performance penalties, at least for your collective operations, could be really big. So for example, here we have tried to do an experiment with bindings and without any bindings. And what we tried to do is we tried to do an all reduce up to 512 nodes, 12 ranks per node with a buffer size of 1 gigabyte. And what we have seen is that at 512 nodes level, the performance penalty to do an all reduce with large buffer sizes, which are typical for our LLM or um, uh, regular machine learning training exercise, the performance penalty can be as high as 27% for 256 nodes. For that particular experiment that I'm showing the result, the performance penalty was 41%. So we have tried to give an optimal set of CPU bindings in our user documentation. So to be performance conscious of your training exercise, we would recommend users to follow the documentation. And finally, we have an experimental module called Frameworks Optimized that we are trying to build and optimize for each frameworks release. Interested users can take a look at that, but this is experimental and we are in the process of building it out. Thank you very much, and that's all I had from my side. And I would stop share and I would hand it over to Sam, who would talk to us about the large language model efforts at ALCF. Thank you. Sam, please take it away.
Sure. So can everybody see this markdown file? Okay.
Yes. Could you make it a bit bigger?
Absolutely. How's that?
I think that's better.
Sure. So yeah, I just sent the link in the chat to this file so people can follow along if they are interested. So for the sake of time, this will be a bit of an abbreviated talk that I gave recently, I guess, yeah, last week at the Insight Hackathon. So there's an HTML and slide-based versions of this content that are hosted on my website that people can look through at their own leisure if they are interested. That'll obviously has the complete content. Given that I've got about 10 minutes or so, this is going to be an abbreviated talk, mostly based on things that people found interesting in the last version of this. So this is mostly about a library that I've been working on maintaining called Easy Peasy. So it's available on GitHub. You can follow the link here. That kind of aims to remove a lot of the headaches that might arise from users wanting to run their code on multiple machines, automatically detecting and using running in a distributed fashion when appropriate. Really with the kind of goal being that you can write your code once and run it anywhere, with sort of automatic device selection and information about job and world size and these types of things. So I'll mostly be talking through those features specifically and how you can use them on Aurora or Polaris or any of the machines at ALCF. So this was originally presented at the hackathon. So the original point being to get started, submit an interactive job. Then I provide this easy peasy utils.sh script that you can source directly from, so you can use curl to download it and then source it directly in your shell runtime. This has some kind of nice features that will automatically detect things like, how many hosts are available in your job, how many GPUs are on each of those hosts. So this will vary from machine to machine, obviously, but if you do this on Aurora or Polaris or any of the machines at ALCF, you'll get consistent behavior. So on Aurora, for example, it'll automatically detect that you're on Aurora. Um, Based on the fact that you're on Aurora, figure out how many GPUs are on each of these nodes. It'll do things like parse your PBS node file to figure out how many hosts are available in your job, and then use some simple arithmetic to figure out if I have 2 hosts and 12 GPUs on each host, then I have globally available 24 GPUs to me. And if you were to run this same thing on Polaris, for example, where there are only 4 GPUs per host, it would, be smart enough to kind of figure that all out automatically for you. And this defines some nice aliases and things for you to automatically launch across multiple devices. So this is pretty much what I just said out loud. Um, does some really nice automatic detection of where you are and what's available to you. Based on that, it can automatically set up your Python environment and things for you. Again, there's a lot more detail on all of this if people are interested. I know I'm going to kind of blow through it to try to talk about things that people thought were interesting. So most interested, or at least what I get the most feedback on and users seem to be the most interested in, are the Python features. So if you remember from Filippo's talk, if you want to modify code that you have already running on an NVIDIA-based system, it requires explicit modification of cutting out, all of your CUDA calls to XPU devices. And so as a developer who works on all of these different systems, was, kind of frustrated with having to maintain different copies of things for different systems. And so, at a very base level, the easiest thing to do is just abstract away CUDA XPU devices entirely. And you can replace any of those calls with this get torch device type, which will automatically detect, if you're on a CUDA-based system or an XPU-based system. And it will also has fallback to CPU if none of the available accelerators are detected. There's also support for automatic and simple initialization of PyTorch across multiple processes. So again, I'm sure if you will remember from Filippo's example, there is kind of this whole MPI initialization. You have to first get the master host and the master address, broadcast that from rank 0, and then following all of that, do this torch.distributed.initialize process with the correct backend, which is again going to vary from system to system. And so taking advantage of this automatic backend detection, automatic device detection, I can then use that to determine what communications library to use and kind of abstract all of that away from you. And so this function kind of is actually a direct wrapper around all of that complicated MPI initialization that supports, any different, CUDA or XPU. It would also work with multiple MPS. So if you have a lot of Apple devices, you could train across. So it's, kind of meant to be abstract and functional without, requiring a lot of manual intervention from the user. Once you've then set up Torch, you can do things like, easy peasy.get rank to determine the to determine your local global rank across all of your MPI processes. Things like the world size to figure out the total number of MPI processes. Again, you can replace explicit calls to devices by replacing with this get torch device type. I've also got support for automatic single process logging. So if you've used loggers previously in a multi-process Python script, typically, unless you have some manual code in there, it will automatically output from every rank, which is typically not what you want. So I've got some sort of manual or automatic mechanism for only printing out from a single rank, which is convenient. It's also, you can toggle it on and off if you want to print from everyone. I've got support for distributed debugging. So if you have some code that you're trying to debug that is hard to problems only pop up in multiprocessing, fashion, you can use this breakpoint that'll catch everything only on rank 0. So it allows you to, try to interactively debug distributed code in a pretty straightforward manner. Oh, 2 minutes left. There's also support for automatic experiment tracking with weights and biases that people seem to like. So you can call this easy peasy.setup weights and biases. And this will automatically set up weights and biases and everything for you, capturing some information about your environment. And then you can, set this up at the beginning of your script, build your model, optimizer, etc., as you would. Have a train step that returns some dictionary of metrics. And then I can basically just pass that into this update function that will automatically pass everything to weights and biases. So I have a complete self-contained minimal example that has kind of all of these features laid out that I'll maybe try to work through quickly. So as I mentioned, you can create a logger at the beginning of your script, build your network, simple network as you would. I've also got this nice little decorator you can use to time the execution of individual functions. This works through the explicit training of that model. So you can see, for example, I create a history to record metrics of interest during training. I can explicitly get this device type, figure out the data type of my model, make sure everything's on the right device, and so on. Then work through this explicit training loop. So you can see I wrap the explicit model forward and backward calls with this autocast wrapper context manager. So I know the device type and the data type. This will make sure that everything is done on this device with that data type. For the sake of, this being a very simple example, I just create a random input at each step, call the model with that output or with that input, calculate some very simple loss, and then periodically update my history with metrics of interest. So at a specified frequency interval, I'll update my history with current iteration, loss, forward and backward timings, and so on. And that's a, completely self-contained training loop. This works through the setting up of all of that. So like I mentioned before, you can set up weights and biases pretty straightforwardly, build your network, move everything to the right place, simple check to see if I'm in a distributed environment. If so, wrap my model with DDP. And this will work on with any accelerator device at any scale. So you can launch it. I have some additional tools for launching it, even in a distributed fashion. But this is way more material than I could really realistically aim to cover in 10 minutes. So hopefully this was a somewhat high level and interesting overview, and I'll pass it on to Sid. Also around and helpful around for any questions at any time. Thank you.
Thanks, Sam. I'll go ahead and share my screen. Can you see my screen?
Yes.
Yeah, thanks. Okay, so I'll be talking about how do you enable fast inference on Aurora using a framework called as VLLM. So once you have followed all these instructions to train your model and fine-tuned it, and once you have it ready, obviously you can use like a inbuilt library in Hugging Face, which is transformers, to run your inference workloads. But there are many other frameworks like VLLM, which use this technique called as paged attention, where they use this page-like memory organization for the KV cache to make the inference much faster. So we have set up this framework on Aurora, and today I'll be talking about how do you install it on Aurora, and then how you can run some of the models using this framework. So first thing first, like similar to earlier examples today, first you have to load your frameworks module, and then we are going to create this new Conda environment called as VLLM, and then you're simply going to activate that environment. Once that's done, you're going to load some more modules to make sure that we have all the dependencies that are required for this particular version of VLLM. Then for your convenience, like some other dependencies for VLLM are present at this location on Aurora, which should be accessible for all of you. This will basically install other things like particular version of PyTorch that is required for this VLLM. And then finally, I have a pre-built wheel for VLLM 0.6.6, and you're simply going to pip install that in this new conda environment. And with these instructions, you should be pretty much set to run VLLM on Aurora. In addition to this, you can also like install VLLM from source by loading models frameworks, but this is just to make your life convenient. But of course, you can install VLLM from source. Now, once you have VLLM to run any kind of inference, you're going to require the model weights. So the commonly used models, open source models like Llama 2, Llama 3, Mixtral, Quen, or even bigger models like Llama 4 or 5 billion models, they are all those weights are already downloaded from Hugging Face, and they are available for everyone to access at this location. Note that this location is only read-only location. So if you have a custom model, or if you want to run inference on some different model, you need to like download those weights separately and then point these Hugging Face directories to appropriate location. But let's say you have a model like Llama 27B, which is quite common, and you want to just run some inference workload on that, then you can simply point this Hugging Face home dataset cache directories to this location, and you don't have to download those models again in your directory. You will have to set up your Hugging Face token, and the instructions on how to get that token are present on this link. And with that, you should have access to the model weights in this location. Then next, I'll be talking about some of the common configuration recommendations that are good for the performance on Aurora. So the first one is we'll be using the flat device hierarchy as flat. So this will basically enable you to VLLM to see each tile of Aurora GPU as a device. So there will be total of 12 tiles. The next thing that we are going to do is set up the VLLM host IP. So with this command, it will get the correct IP address of the network interface, and it will set it to that location. So make sure this is part of your submission script, or when you're running, make sure you're setting this up. And VLLM uses something called as array for a distributed runs, and by distributed I mean multiple tile runs as well as multiple node runs. So if you want to run anything that is going to require more than a single tile, then setting up a array cluster is important, and you can do that with this command. It's the simplest form of that command. So these are the common configuration options for VLLM. Then I'm going to showcase how do you run like some small, medium, and large models here. So to run a small model like Llama 27B, which has around 7 billion parameters, Aurora single tile has a 64 gigabytes of memory, which is enough to fit this entire model along with KV cache and all other model parameters onto a single device. So you don't even have to set up a array cluster here because we are not doing anything distributed. So you can simply call this command like VLLM serve, the name of the model, particular port number, device like you want to run it on XPU, and a particular data type, and you should be serving your model with this command. It's quite straightforward. But let's say you want to use multiple tiles, then as I mentioned earlier, like you first have to set up this array cluster. So for that, you have to set up this VLLM host IP, and you have to first start a array cluster, and then you follow the same command. You can do this with like you don't need to do this for small model like 7 billion parameter model, but for a bigger models like a 70 billion parameter model, you will not be able to fit it on a single tile, and then using multiple tiles becomes important. So that's how you serve like a small and medium sized models. Now, when trying to serve larger models, like for example, Llama 3.1405 billion model, it's not like a single node, even with 12 tiles, is not enough to fit that model. So in that case, you have to use multiple nodes. Now there is additional step required here. So basically you have to invoke this script called as setup ray cluster. So this will basically whatever number of nodes you have asked job scheduler, it will go there. It will start a head node on one of the nodes and the worker nodes on other nodes. And once this ray cluster is set up with this shell script, which is again present in the same repository here at the top, setup ray cluster, then it will set up this cluster. And then again, once the setup is done successfully, you're simply going to use the same command, but with the bigger model size here. And that should be good to go. Now, if you face some issues like you're running out of memory or something, so that's typically because you're not able to save your entire KV cache into the GPU's memory. So in that case, use this parameter like max model length to something like 32,000 or 60,000, 50,000, because by default it will take model's maximum context length, which is going to be 128K, and then you will require more than 2 nodes. So for example, to run this 405 billion model on 2 nodes, you have to set this to like a smaller value, like 8K or 16K. Now, what happens once you serve the model? So for that, I have given some examples. Once the model is served with, for example, a Llama 2 7 billion model, now you can give it some prompts and you can expect some response back. And that can be easily done using OpenAI's API. And this one OpenAI example.py script basically shows that. If you want to run some benchmarks and try to get some numbers, then again, the first step is to like serve a model, and then you can run this offline benchmarking script, and then you can get some numbers like what's the throughput for various stages. So I have again provided those scripts to quickly go through them. So using one API is quite easy. So you basically set your API key as empty and give the local host 8000 as the port number there. And then you say which model you want to use and some prompt to it, like you're a helpful assistant and tell me a joke. And it will produce some chat response that you can just print out. This is the simple like hello world. Once you're done serving the model, you can run this script. In addition to that, if you're interested in offline benchmark, then like similarly, you can go through this example where you can set which model, what is the maximum tokens, input length, batch size, etc., parallelism, and you can get some performance numbers. Similarly, also feel free to go through this setup cluster.sh script where we set up multiple parameters to run this successfully. And yeah, so yeah, that's all I had to show in 10 minutes. So if you have any more questions, please feel free to reach out to me.